Huffman codes. Usually we wish to compress a file when the file size is large. So these Huffman codes, it develops codes for reducing file sizes. That is what you say file compression. Supposing you have a file of size 100 MB, file size. I want to compress it. And make it file whose size is less than 100 MB without loss of data. Without loss of data means the file compression without loss of data. So if you want to do this file compression without loss of data, there are two phases. So you have a file, you compress it using Huffman codes. This using file compression using. And the other end, again you restore the file. Restore the file again using the same Huffman codes. You can restore the file using the Huffman codes. So when you look a little details into this, if you observe any file, especially the text file, text containing different characters of English, let us say letters A, B, C, D, E, etc. It may also contain the digits 0, 1, 2, 3, 4, 5, etc. So, what is the process of this compression? If you go for the compression process, you first make a statistical analysis of statistics of letters of a text file. Let us say A appeared some 500 times in a text. This is letter and this is the frequency. And let's imagine that B appeared in a small text, something like 100 times, and C appeared let us imagine that some 150 times, and D appeared around 125 times, and E appeared around 400 times, and imagine some other letter like F appeared something like 110 times. So these are the letters, and there are many other letters appearing, but let us take for this. You know that for coding purpose, every letter is represented in ASCII format. So each letter takes 8 bits. So letter A, 8 bits. It appeared 500 times. So that was 4000 bits. Letter B appeared 100 times. So 8 bits each. So 800 bits. And again C, it appeared 8 bits. It appeared 150 times. And D, it appeared 125 times. And E appeared 400 times. F appeared 110 times. So if you observe here, for each of the characters, each of the letters, you are taking 8 bits. And it's always the multiplication, how many times it appeared. So it's all the multiplication. What normally done is, so this has taken 1200 bits. So this has taken 1000 bits. This has taken 3200 bits. And it has taken 88 bits. However, you can total all this and so some figure like it has appeared like this. So what we do in case of Huffman coding is, if you keep these letters, that once again the same, you say A appeared, as I just now listed, A appeared 500 times, B appeared 100 times, just now this, just frequently. So C appeared 150 times, D appeared 125 times, E appeared 400 times, F appeared 110 times. So what I do is, in the Huffman coding, first I take the characters which have appeared less number of times. So if you arrange them in the descending order, so this is the lowest is this 100, then the second lowest is this F. So what I do is, I construct a binary tree using these letters and taking into consideration the frequency of these letters. So first what I do is, I pick up the 2 letters which have the least number of frequencies. So coming by that, say B appeared 100 times. Now I create a node, I create a tree node, and I write here B, I say it is 100, and another node F, which has appeared 110 times. So now, if you consider this 110 and this, it is 210 here. So now what I do is, again this is processed and this is also processed. Now this 210, 150, 125, 400 and this one. Now the next 2 least numbers are this and this. So I construct another binary tree with the nodes one side containing C, it is 150, the other side it is containing D, 125. So now this 150 and 120, so it is 275, and I name this as, it's only for the purpose of naming, no specific meaning for that, Z1 and Z2. Now this is also processed and it is also processed. Next I pick up two smallest numbers. So the numbers now what I have is, the letters I have is A, it is 500, and E, it is 400, and here I have some two other trees which have been already constructed. This is 210 and 275. Now these are the only two small elements, therefore I construct a binary tree with having Z1 as one child, Z2 as the one child for this. So now if you see this total, it comes to 485 Z3. Now there are now three. One is A having 500 frequency, E having this, and this a tree containing 485. So now we need to consider these two. So I write this Z4 and I make this E appear here 400. So now it is 885. So this is also processed. Now the only two things left over are this A and this. So this is also I construct another one and making this as A, and it is 500. So if you now observe this, all the letters of this text, they appear as external nodes for this binary tree. In my encoding process, what I do is, if it is a right child for a node, take any node, internal nodes, these are internal nodes, any right child you put it as 1, left child you write it as 0. Now this is 1, 0, and this is the right child for this node, I'll put it as 1. This is the left child, put it as 0, and for this node it is the right child, I'll put it as 1, and this is the left child, I put it as 0, and for this I put it as 1, and for this I write it as 0, and for this the right child I'll put it as 1, and this is 0. Now if you observe this, all these letters are appearing as external nodes. This is our root. If you observe the codes, so I write here letter and the code. Going by this A. For A, you have only one bit, that is 1. If you take E starting from the root, you have to go left and then right. So it is 0, 1. Now coming to D, if you take up this D, you have to start from again the root 0, 0, 1, 1. So 0, 0, 1, 1. So if you talk about C, for C it is 0, 0, 1, 0. 0, 0, 1, 0. See, now for F, 0, 0, 0, 1. So for F, 0, 0, 0, 0, 1. And for B, start from here, 1, 0, 0, 0, 0. 0, 0, 0, 0. So if you observe here, the same letters A, E, D, C, F, B. This is the code for A, it is the code for E, it is the code for D, code for this. And you also observe that no code is prefix of. No code is prefix for the other code. Observe that this is 1, and none of the codes is beginning with 1. And this is 0, 1, and none of the codes is beginning with 0, 1. And this is the code for D, and none of the codes is beginning with 0, 0, 1, 1, 0, 0, 1, 1. And this is for this 0, 0, 1, 0, these codes are. So this clearly says that you can encode any text without much confusion. Now if you want to encode a text like fade, so the code for F is 0, 0, 0, 0, 1. For A, the code is 1. For D, the code is 0, 0, 1, 1. For E, the code is 0, 1. If you see the advantage of this, in your ASCII you are sending 8 bits, but here it is now only 1 bit you are sending. So there is a saving of